right, we need, before I continue, a few administrative remarks, right? The first one concerns the written examination. I told you about that. Don't be surprised now. You know it. There is a written examination at the end. I never promised anything else, okay? So it's the written examination. It'll take place on Monday, February 7th. That's the first Monday after the term ends here, between 10:15 and 12, and it'll be in the lecture hall F005, the so-called Blaue Grotte. The Blue Lagoon. No, it's not a lagoon. It's Blaue Grotte. I don't know what a grotte is. It's a cavity, right? A blue cavity. Whatever it is, it's down there, 10 meters. I just checked the room number. It's indeed F005. This one has E11, and this one has F on the same floor. I don't know the logics. Please don't ask me. But I know it's over there. You'll find it, right? If you don't find it, ask your intelligent neighbor, right? She will know. And she leads you, holding your hand, not for romantic reasons, but for leading you to the written examination. So that's on Monday, February 7th. The thing that will start in a week from now, in 2 weeks from now, is the presentations. And what I'm going to say about the presentations, which will be all your job, I will keep quiet, not all the time, but some of the time at least. That's where during the time when you talk. Okay. I said already in the beginning of the lecture course, I said something about these presentations, and I'm going to say a little more now that it becomes concrete for you to work on these papers, and that holds in principle also for those who hand in papers, right? The people from the water resources and environmental management, because they don't give the oral presentations, but they have written examinations. The structure of these both papers and oral presentations is the following. You have first a short section where you describe your research project to someone who doesn't know your research project. For instance, me. I don't know your master's thesis. I don't know your research project. So you've got to tell me what the research project is. For the oral presentations, that's a maximum of 5 minutes. It must be not more than 5 minutes. Do you understand the number? It's 5 minutes and not more, okay? For the written presentations, it's 1 page, right? With a normal font, right? Don't take a 3-point font where I use a microscope to read it, right? I won't use a microscope to read it. All right, so 1 page or 5 minutes. Then the second part is also in the oral presentation, 5 minutes, also in the written presentation, maximum 1 page. You connect your research project with the 4 positions, or 5, how many positions did we discuss? 4 positions, right? 4 positions that were presented here: inductivism, deductivism, paradigm theory, and systematicity theory. And here you have a choice. You have 2 ways, and you have to pick one. Or you may, well, even in between if you really want. One is that you go through the 4 positions and say why this position doesn't fit your project and that position does fit your project, right? You say, okay, I'm not doing inductivism in my project because I test the hypothesis, therefore deductivism would fit, right? It would describe somehow what I'm doing. Paradigm theory does not fit, and for instance, systematicity theory does fit, or whatever it is, right? You simply discuss all the 4 positions with respect to your project. That's one possibility, right? You may choose this one. Or you may choose a different procedure in which you discuss only one of these positions, namely this one that fits your project best, right? You say, you know, my project is this and this, and when I compare that with, say, paradigm theory, then you see the following elements of my research project really fit with paradigm theory, and then you describe your research project in terms of, for instance, paradigm theory, or whatever it is, or inductivism or systematicity theory, right? In that particular case, you only discuss one of these philosophical positions in connection to your research project, but you should take this one that really fits, right? It may be that your research project doesn't fit any of these, or it may fit all of these. I don't know. That's your job to find out, right? You understand, hopefully at least, the idea behind that format. You should think about your research project in light of these philosophical positions, and at the same time, you should think about these philosophical positions in terms of your research project, right? You learn something about both, that's the idea, right? You learn thinking about your research project in a new way, and you also make these philosophical positions more concrete by applying them to your research project, right? And you may choose either way, either discuss all the four, then of course you have not very much time, right? You've got 5 minutes, right? Then you must quickly kill 3, for instance, and then discuss 1, right? Or you may also discuss only 2 or so if you really wish for some reason, okay? But then possibly I ask you, why didn't you discuss the 3rd one? And then you must give me an answer, like, well, a good one rather. If you just say, oh, I didn't like it, that's possibly not enough, okay? Should be some sort of argument, okay? All right, is that comparatively clear? And I tell you, we have 6 presentations per sessions here. So we have twice 3/4 of an hour, and I must stop you after 15 minutes because it would be unfair to the next person who follows, and we don't have more time, right? This puts some pressure on you. Also, this pressure is intentional, right? I'm not torturing you for no reason, but I have a good reason why I say that, because you have to learn to make concise and short presentations. You will need that in your professional life that is about to come, sooner or later, hopefully this year, right? You have to learn that. You have to be able to communicate effectively. And there will be situations in your professional life in which you have to be able to present something within 5 minutes, and much can depend on that. And therefore, it's useful to practice that at a university where you can learn something and where it doesn't cost too much when you fail, right? And as you then see 18 or something presentations, and I will also comment on the quality of the presentations, whether you solved this problem, right? So you will learn something about presenting as well. That's the idea, right, of these presentations as well. So we have a package really, a learning package. You learn something about your project, you learn something about the different positions, and you learn something about how to present, right? And that's why we have these sessions. And I can promise you that the students of former years were very satisfied with that format because they really thought that they learned something. Okay, just that you know, I know that it's pressure, I know that you will be nervous before, I will take care of that as far as I can. I know it's some pressure, but that is simply part of the game here, and it does make sense to exert this pressure on you, just that you know what's going to happen here. I'm treating you now as a doctor. A good doctor teaches patients. He tells them beforehand what's all going to happen, right? That the patient, oh yes, it's painful, but it's for a good purpose, right? That's the idea, right? Okay. Any questions regarding the presentations? Right? And the written presentations as well. Don't exceed 1 page, presentation of your research project. And I must understand it. You know, I'm both ignorant and stupid. So you must write very clear, right? Otherwise I don't understand what you're writing about. And I must be able to understand it, right? And I'm neither a water engineer nor a plant physiologist nor an economist. So you must write clear. That's also a situation which you will find in your professional life. You will have to talk to many people, which to your colleagues you say he's an idiot or she's an idiot, but still you must convince him or her, right? And you must be clear enough to convince him or her, right? That you have a project that's worth pursuing and you get the resources and blah, 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 and it's for a good political purpose or whatever it is. Okay? Right? Any questions? Any pressure? Don't worry about it. All the generations of students that I've accompanied here, they all did very well, and you will do very well as well, even if you're now a little nervous, no problem. Okay? Further questions about the presentations? No? Pretty glass clear? Yeah? For those of you... Oh, that's what I said. I think it's February 2nd at noon. I think. Didn't I say so? Yes. Electronically, please. You may also hand, if you really wish, you can give me a piece of paper. That's the last session we are having here, right? Wednesday, February 2nd, if I'm not mistaken, yes. At noon, right? So if you finish during the lecture course, you start typing your presentation, but at noon it's got to be here, right? So send it in to me. You got my email address. Okay, clear? Good. Any other questions concerning that? Okay, then we can continue here with systematicity theory. What I explained to you was that the fundamental thesis of systematicity theory has to be expanded, or developed rather, such that it becomes explicit, what I did here, that it's supposed to apply to 9 different aspects of science, 9 different dimensions of science, if you wish, or properties, not properties really, it's really aspects or dimensions of science, and these are the dimensions. I discussed them quickly to give you an overview, and now you see that the systematicity theory is not that simple, you know, it's not just one sentence which you have to argue for, but it really decomposes in 9 different areas, so to speak. And that is what I have to do next then. And that's a rather formidable task, namely that a complete justification of the fundamental thesis of systematicity theory has to show that all sciences are more systematic than everyday knowledge in all 9 dimensions. And I wrote in italics here, all sciences in all 9 dimensions. So all sciences, so how many sciences are there altogether? Do you have a guess how many sciences, including the humanities? How are there? 2 or 1 million or 50 million? How many sciences are there? Have you any guess, any number, any guess? What's your guess? Or do you know it? Have you learned it somewhere, how many sciences there are? Did you learn that at home, in some class? No, the number is not good, not well defined. I mean, okay, give me a guess. Any guess? How many sciences are there? 3? 100. Yeah, go. Don't worry. You say 100. Okay? 100. Yeah. That's what you say. Okay. More or less, some other guess? 3. 2. What is it? The 2? You can name it. 100 is too long, but tell me the 2. What field are you in? Yeah, water engineer, right? So it's water engineering and environmental management. These are that's a little narrow-minded, I tell you. That's too little. 100 is a better guess. So any other guesses? Would someone go for 200? Someone say, no, 100 is not enough? No? Everyone agrees it's 100? Maybe 1,000? Okay. 1,000. 1, 2... No, anyone in between or less than that? What's your guesses? More than 1,000? No? No more guesses? But don't worry. You can't do anything wrong. I remember your faces anyway, you know. No? Maybe like 1,000. Well, you are not too bad. First of all, there is no official number whatsoever. You can look in different contexts, and what you typically find is numbers between 250 and 600. That's the typical number, but now we have a problem. What does count as a science? I mean, physics, for instance, has many subdisciplines, right? And a science itself is already, it's a not very well-defined expression, or disciplines. How many disciplines are there? But whenever you come to that, and there are many sources where you can look at that, when people have to count the number of sciences, then the typical numbers is between 250 and 600. Now we have a deeper problem here. As I said, it's not only that we have just disciplines, but we have fields of research, smaller units within, and they are quite different from each other, right? Subfields. Even the terminology in English or in Germany is not, in German, is not well defined. The terminology, how to call these subfields or whatever they are, subdisciplines or research areas. There are many words. It's not well defined. People talk in a very unorderly way about these things. Now, there are only very rough guesses. If you cut down now disciplines into these subdisciplines or fields of research or whatever you call them, then you end up with a number usually in the order of magnitude, well, usually there are only two figures I found, 8,000, right? Roughly speaking, 8,000. So if you look then, say, if you look at some area, say, of chemistry, then you don't only have protein chemistry of one of these subfields, but also smaller units within protein chemistry, right? And it makes sense to distinguish them. So however one does that, it's all very fuzzy. But just the order of magnitude is here important, that we know what we are talking about. If we talk disciplines, we talk always several hundred, right? Say, take home something like 300 disciplines. And if we talk about a more fine-grade division of the sciences, then we talk several thousand, more nearer to 10,000 than to 1,000. That's the rough idea. So you see how complicated all of science is. It's a huge thing. It's incredibly huge how many areas there are. And it's almost, I mean, it's absolutely impossible. No one oversees all of that. It has a really cognitive control of that. So what you see here is that the complete justification of the fundamental thesis shows that in all sciences, say in all subdisciplines, that's 8,000, you have to show that everyday knowledge is less systematic in all 9 dimensions. That's 9 times 8,000. That's a very large number, right? 72,000 theses you have to prove or to show. That's impossible, right? And that is the price one has to pay, because systematicity theory is a descriptive theory, right? It says, systematicity theory, I describe what the real science is. And the real science is some 8,000 subdisciplines, and then systematicity theory claims, look, these 8,000 subdisciplines are in 9 different dimensions more systematic than the corresponding everyday knowledge. That is unfortunately so complicated, but that's the price. If you want to have a theory about something that's very complicated, the theory itself will also be somehow very complicated, because it has to cover all the complications of the object or the subject matter that you are describing. So that is unfortunately the price, but that is the price has to be paid. Now, of course, this is impossible. I cannot do that. Nobody can do that, of course. So one has, in order to justify systematicity theory, in order to argue the higher degree of systematicity in the 9 dimensions, one has to use examples. Of course, one cannot run through all these 8,000 subdisciplines. That's absolutely impossible. But one can run through examples from various areas of science, right, and the humanities and mathematics and everything. And that is what I'm going to do, and that will take the remainder of this class before the presentations start, the next 1.5 hours, or 1.5 hours. I will go through the 9 dimensions, and I will give you examples from very different fields of science that show you that it's extremely plausible what systematicity theory claims, namely this higher degree of systematicity in these 9 dimensions across the board through all sciences. Okay? And just to let you know that, you, of course, you don't have to remember all the examples. That doesn't make sense. I'm not teaching you here, science in general, and you have to remember all the examples. Some of the examples will be completely new to you, and just for the written examination, don't worry too much about it. You should know some examples, right? So the worst I will do in the written examination, then I ask you, give me 3 examples, right? But you should follow here in order to understand the main thing, namely systematicity theory. And in case you want to apply it to your own master's thesis, so better be careful now and watch out and remember what's going on here, because you may use it, okay? So, I'm coming now to these 9 dimensions of systematicity that I gave you the list of earlier. And what has to be done now, it has to be shown that science is more systematic than everyday knowledge in all the 9 dimensions. That's the program, right? You understand the program? That's part of the justification, or that is the main justification of systematicity theory, to show you that systematicity theory is a good theory of the sciences, because I can show you that in all the 9 dimensions, at least in the examples I'm presenting, that scientific knowledge is more systematic than everyday knowledge. Okay? That's the program. Such that you now have a clue why I give you these lots of examples that I'm going to give you now and in the next session. Okay, so we start, of course, with descriptions. I'm running through the list now, the descriptions. Now let us look at mathematics first. Mathematics is also a science. It's not an empirical science. It's another form of science. I don't know whether you learned that sometime, be it in high school or be it at the university, that the formal sciences, the classic formal sciences, just think of mathematics. Think of geometry or whatever you think of as a subfield of mathematics. What is done in mathematics, you describe a certain field by axioms. That is the fundamental description that you get in mathematics, always. You get a set of axioms. And the axioms are just fundamental sentences describing the objects you are treating. So, for instance, in Euclidean geometry, you get a set of axioms that concerns points and lines and planes. And you get axioms about that, right? Or if you have number theory, you want to describe what the natural numbers are, you get Peano's axioms, and these axioms describe these objects, namely natural numbers. And what mathematics, what is the practice of mathematics then, is that you prove theorems, statements, on the basis of the axioms. Right? The axioms are the sentences you can take for granted because they define the area you are talking about. And when you state something then about the objects of this area, then you try to formulate a theorem, and the theorem becomes a proven theorem once you can derive it from the axioms. Right? You give a proof for the theorem on the basis of the axioms. But the fundamental description of your objects, be it natural numbers or geometrical points or geometry or whatever it is, or groups or rings or whatever mathematical objects are, they are described by axioms. And the axioms must be logically independent from each other. They must be absolutely independent, and also there are 4 postulates on the axioms. I'm not going through them systematically, I'm just giving you the idea. The axioms must be complete as far as it goes to describe the area you're discussing. So what you have in mathematics is an extremely systematic description of your area by means of axioms, logically independent axioms that describe as complete as possible your area you're discussing. So mathematics is, of course, a wonderful example of the systematicity of science. Already regarding the descriptions, but you will also see that in the dimension of the defense of knowledge claims, the proofs are also something extremely systematic, and it's not an accident that some people think, when they think of science, that mathematics is the highest form of any science ever achieved by humankind. It's mathematics as the prime example of what scientific knowledge is all about. Absolutely secure knowledge and absolute transparency, that you understand just everything. Well, if one looks extremely close, you don't understand really everything, but as far as human understanding goes, mathematics is an extremely good example of science. And therefore, it's not surprising, if systematicity theory is right, that already on the level of descriptions and the dimension of descriptions, that mathematical knowledge is extremely systematic, namely by an axiomatic description. Okay, is axiomatic description and axiom something completely new to you? Some of you never heard of it, what an axiom is? Yeah, admit it, don't worry. I remember your faces anyway, as I said. So anyway, if you don't know much about it, then you learn something new. If you know something about it, that's something. It's a very, as I said, extremely systematic description because you have very few axioms. So for instance, in Peano axioms, I think there are 4 axioms. Something. And it's always a small number of sentences in which in principle, all the knowledge about the area is contained. And you only have to tease it out by articulating theorems and proving them on the basis of axioms. Okay, that's mathematics. Now, that'll be like in the evening news, right? Every 30 seconds, something new comes. Politics, sport, weather, blah, blah. And here, now we switch immediately to the next area. That is namely classification. Classification is something we do also in everyday knowledge, of course, but we also do it in the sciences where we have large number of any sort of objects and we classify them. That means we put them in different classes in order to describe them, right? And we have, for instance, classifications of mathematical objects. This is, I'm not going into details, of biological species. At the moment, as far as I know, the number of biological species alive or extinct is in the order of magnitude 10 million, right? That's today's biology. It's 10 million different species. It will be many more in the future because many, 95% of all the species are extinct. This is a process that's not at the end. So these classifications and hierarchy, and the hierarchy even is not at its end, and biological species is 10 million, right? So you have to have a very complicated form of classification here. Minerals are also classified. Chemical elements and compounds. You know, if you look at the periodic system of the chemical elements, here you hear already periodical system. It's a system, right? It's not just somehow collected, but it's systematically ordered. That's the periodic system in which you have all the elements, 1 to 92, right? All the stable elements are in there. And also in the compounds, you have complicated classifying schemes in order to classify the compounds. Compounds are also the order of magnitude, just to let you know what today's chemistry is, also in the several millions, right? Several millions compounds are known in science, in chemistry. And of course, if you want to have an overview and describe them, you must do that systematically, otherwise you don't stand a chance to achieve anything, right? You must find these compounds, you must be able to look them up, and of course you need a very careful classification. Also concerning languages, for instance, also very interesting. Do you have a guess how many languages exist? Any idea? Again, you come with 100, right? You come with 2. German and your home mother tongue. No, that's too narrow-minded. Okay, how many languages? What would be your guess? More than 100? 1,000? Okay. How many? 1 million. 1 million languages. Okay. Well, the official number is something a little more than 5,000. Okay, there's of course a problem with the dialects, right? The difference between a dialect and a language. I don't know how this difference is made. You see, that's, by the way, that's of course very similar to the difference between scientific disciplines and subdisciplines, right? Because the subdisciplines, in a sense, are dialects, right? If you have a subdiscipline, say, solid-state physics, and that's, of course, it's physics, but it's a sort of dialect. They speak a little different from general physics. So it's a sort of dialect, and there you have, of course, the same problem of demarcation, of saying what's the main thing and what's the dialect. And that's the same with languages, as far as I know. So languages are, languages are life, one must say, still alive languages. And then in the order of magnitude of 5 million, you can all find that on the internet, by the way. There's a classification of languages. It's updated every 5 years. And we are in the order of magnitude of 5,000, 5,500, I think. Then forms of governance, for instance, are also classified. Literary genres are classified. Whatever. There are many, many sorts of classifications in science. And of course, the basic idea of classification is you have a lot of objects, you have many objects, and you must have an overview because you want to describe something. You want to describe the objects. And one of these ordering devices is, of course, classification. And of course, classification is something systematic, right? You put something in boxes, not at random, but systematically. And classification runs through all the sciences, right? You find it almost everywhere. Classifying the objects, especially when you have many objects, you have to classify them. Of course, in physics, also elementary particles, all that is all classified. Not classified in the sense of secret, not classified information. No, in the sense that the objects are put into classes. And their classification. So this is also an ordering device that increases the systematicity of descriptions. And of course, you find it in science everywhere. Then you have something that is also extremely important in the sciences, and that applies to, I guess, every one of you, namely quantification. That you give descriptive statements, you describe something in quantitative form, right? You count it or you measure it, right? why is this a form of, why does this increase the systematicity of a description? I give you a very simple example. When we talk about the weather and about the question how warm or how cold it is, if we do that in everyday language, you may say, today for a winter day in Hanover, it's fairly cold. Right? That's a meaningful statement. Or you may say, oh, it's pretty cold, you know, or when it's really cold, you say, oh, it's bitter cold. Or you may say, it's extremely cold, right? Or when it's warmer, you may say, oh, it's a moderate temperature today, or it's a little warm and nice. And then you say, oh, today is pretty warm. Or you may say, oh, it's fairly hot today. Or you may say, it's extremely hot. Or you may say, it's unbearably hot, or whatever you say. Okay. So when you look at our language, how we do that, you may come up with something like 20, 30 expressions, right? If your English is poor, you come up with 5. If your English is very good, you come up with 20. And in your home language, you may perhaps come up with 30. I don't know. That's the order of magnitude, right? The problem is it's not very well ordered, right? When you say it's extremely hot, is that hotter than unbearably hot? Or is it less hot? Difficult to say in language. That's not very clear, right? It is somehow systematic. There is some sort of ordering, but it's not extremely systematic. Now, use a scientific instrument, a thermometer, right? You spend €2 of your stipend and go to a shop and buy a thermometer for €2, right? And immediately you can give something like 600 ordered descriptions, 600 precisely ordered descriptions about the temperature outside, say from minus 25 to plus 35 degrees, and a cheap thermometer has an accuracy of 1/10 of a degree centigrades, right? You can say between minus 25, minus 24.9, minus 24.8, all the way up to 35, for instance. Then you have 60 degrees or 600 degrees, 600 in intervals of 10th of degrees. So you have a quantification of temperature, and you get immediately 600 in this very primitive sense, right? In this very primitive way, 600 perfectly ordered descriptions just by quantification, okay? So you see what the use of quantification is regarding descriptions. You add systematicity incredibly easily, in a sense, when you use a thermometer, when you have a good variable to measure, namely temperature, for instance, and going from 20 or 30 rather vague qualitative descriptions like fairly hot, fairly cold, blah, 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 or that, and you switch to a quantitative description and you add an incredible degree of systematicity, very simply. You know, they are all perfectly ordered. It's absolutely clear that minus 25 is colder than minus 24, and plus 19.8 is warmer than 19.7, right? It's perfectly ordered, so it's very systematic, and it's very well defined. You know what you're talking about when you say 19.8 degrees. You put out your thermometer, you wait for a minute or whatever it is, and then you read it off. And someone else who has the same thermometer does the same, reads off the same number, right? The description then of the weather state regarding its temperature becomes extremely systematic by having a measuring instrument and a quantitative scale for temperature. So you see immediately why quantification is such an important device in science, because it adds to the systematicity of the description in an incredibly strong way. And that is one of the reasons, I mean, this is pretty obvious to most of you, perhaps you never thought deeply about it, why quantification in the sciences is such a highly valued goal, because you add so much already regarding the descriptions. I tell you later regarding then the defense of knowledge claims, that also their mathematics, or the quantification and the mathematics that can be applied to them, is extremely important in order to push the systematicity, the degree of systematicity in science higher, and that is what science intends, right? So the successful quantification of descriptive statements gives you a higher accuracy and more order, and all that is more systematicity. I write here successful quantification because some of the attempts of quantification, especially in the social sciences, are not very successful, and also sometimes in the natural sciences. There are complicated theoretical problems behind that, in what cases a quantification can be successful. It's not always successful. Don't worry if you for instance, just a discussion about, say, intelligence, the quantification of intelligence, by the IQ, the intelligence quotient, which is a number, right? 100 is the mean, and 120 you are fairly intelligent, and so on and so forth. And that's a very controversial subject because it's not really clear that intelligence can be quantified in that way. And you find in many areas of social science, in many, many different areas, political science, psychology, sociology, in many areas, also economics partly, but there is less severe usually. You have problems with the quantification, so the quantification must be successful. And I'm not unpacking what that all means because it means a lot, right? Okay, so but when you are successful, or if you are successful, then you gain a lot of systematicity, and you see immediately that all the scientific descriptions that are quantitative, where our everyday descriptions are only qualitative, are of course immediately more systematic. So you see immediately that the thesis is correct with regard to all the quantitative statements, as long as they are successful. That's very important. As long as they are successful in science, then you gain much of systematicity. Okay? Now here's another device that also concerns, I guess, all of you, both the engineers and the scientists, empirical generalizations, where you have phenomenological laws, where you have a general statement, a general description that does not only apply to one particular thing, but applies to many, many things of the same sort. So the example I gave you already quite often was, I think, the law of ideal gases, which is such a law that was discovered in the 17th century. That's the pressure times the volume is, well, let's write it more complicated. It's the number of moles times a certain constant times the temperature. That is such a phenomenological law. It's a general description of a certain class of gases, right? This law tells you that the pressure times the volume that's the amount of gas that's in the container, that's a constant, and that's the temperature. So that if you increase the temperature, for instance, then this one will increase as well, and if you increase this one and you keep this constant, then this must decrease, and so on and so forth. So if you press it, if you increase the pressure, then the volume, if you increase the pressure, the volume will become smaller if you keep the temperature constant, and so on and so forth. This is a state equation for ideal gases. What you have in most of engineering, where you have tables or you have it on the computer nowadays, is of course these sort of state equations, right? The empirical generalizations of a certain behavior, right? If you talk about materials, for instance, how they behave when they break, and the different sort of parameters that you have. Usually these sort of general empirical generalizations, they are extremely important. They presuppose, I'm not going into details, adequate classification, because if you wrongly classify, you don't get empirical generalizations of that sort. But you see immediately the point is that such an equation describes a huge class of different systems at the same time. And therefore it's much more systematic because you've got one equation for many, many, many different sort of systems. And that's of course a generalization that increases the systematicity. We do in everyday life the same, although most of our generalizations are fairly stupid. Many of them say, if we speak about white people and black people, for instance, as if this was a meaningful classification apart from skin color, right? Concerning the human beings, it doesn't tell you anything. It's just a prejudice, right? Or long hair or short hair, whatever. Or blondes and not blondes. Well, blondes are not a problem in this class here. At any rate, you know the jokes about blonde women. And you don't know them? Blonde women in especially America are supposed to be stupid, right? I mean, it's really stupid. At any rate. So we have in everyday life, we have our generalizations. Most of them, I think, are not very good. But of course, what science tries to do is have good generalizations. And of course, it simplifies life if you have generalizations, because you have a more systematic descriptions, you don't have to look at every single case, right? You just know it's a case of this, therefore the generalization applies. So it adds systematicity. And finally, do I have one? Yeah, and here's something else, that you have periodization. That is something in the historical disciplines and also in development, when you say you have a certain development of something and then you distinguish periods, right, between. So you have periods, say, the periods in world history, the ancient times, the Middle Ages, and modern times. Antiquity being, say, from whenever until, say, the year 500, and then from 500 to 1500, roughly, the Middle Ages, and then modern times. This is all controversial, but that's not the point. The point is here that periodization, by describing periods of historical processes, you add systematicity, right? You make the description more systematic. And that is used in many, many sciences. Again, and finally, but I'm not going into detail here, more general historical descriptions, they have a certain structure. If you have a historical description, say, of the development of Africa since the decolonization, for instance, then you have a historical description. And if you look at these descriptions that historians give them, these stories that they tell, they have the same structure of everyday stories, but they are more disciplined. You know, they have more order in it. They are more systematic, and that ends both these subchapter here of descriptions that is supposed to show you that in science, on the level of descriptions, there are many, many devices how to make these descriptions more systematic. And this is what I was supposed to show, that you get an idea why scientific descriptions are more systematic than our everyday descriptions. And I run here through a real large number of disciplines, and having some of these, say, for instance, the device of classification, that's almost universal in the sciences, it's used almost everywhere, and therefore you get a feeling why scientific descriptions, by using all these devices, why scientific descriptions are typically much more systematic than descriptions in everyday knowledge. And that, of course, is then a justification for the thesis of systematicity theory regarding the first aspect here of descriptions. So that's the end for today. Next time, the last regular, so to speak, session where I'm the main actor will be the discussion of the remaining 8 dimensions. And I wish you wonderful 8 more days until we come to this session. Thank you.